Hello, this is AJ1 and this will be our redo for the autocomplete project.
Okay, so we are most proud of the sequential search is the parts that like how easy it was to implement add all method by using an array list. Next. And for binary search, we were we were most proud of the implementation because it performs binary searching instead of like linear searching like sequential search. So this is pretty efficient in terms of time complexity. Next. For the TST part, we like the put method in TST implementation the most because it recursively adds new data to the tree, and this idea was also used in the other method in TST. Okay, and we got to the asymptotic analysis. For sequential search, in whatever cases, add all calls the add all method of an array list, which gives out a data of one runtime. In the worst case, where everyone is a match for all matches method, they will move every single item again into the result array, resulting in one pass two array where you move everything, which gives a worst case runtime of data of n for all matches as well.
Yeah, and we should be clear here that we are assuming that a constant number of terms is added to the data set. So since the sequential search would be theta with respect to how many terms we're adding, and since how many terms we're adding is constant, that's because of this assumption, that's how we got theta of 1. And for binary search, the reason why it's theta of n log n is because adding all method is supposed to sort all the elements immediately. So if n is the amount of elements already in the structure and we're adding a constant number of terms, we have to sort n elements first. So that would be an operation that at best, since comparison sort best case is n log n, we would have to have an n log n we would have to have n log n many operations first, and then we would have to add a constant number of terms. But since n log n is greater than that, the worst case would be bound by theta of n log n. Okay, so for all matches, this is the same case as sequential search where we're doing one pass through the array and copying every single element into a result array list to be returned. So if n is the amount of terms already in there and we're looping through all of them, then this would be theta of n2. Now, for the TST, adding all elements would be theta of n, and that is because in the worst case, we would have the spindly tree, and the height of the spindly tree is the height of the spindly tree, if n elements are already in the spindly tree, would be n, because you're only going to go in one direction only. So adding a constant amount of elements will require you to traverse n elements all the way down, and then adding the constant amount of terms. Therefore, the work that you're doing is theta of n plus a constant amount of work. So the overall runtime, worst case, would be theta of n. So for all matches of the TST, this would also be theta of n because we would start at the top of a assembly tree, copy that term, traverse down by 1, copy that term, and repeating that all the way until you traverse through the entire n levels of the spindly tree, and therefore traversing through n elements like before would also give us theta of n. And for tree sets, we know that this is implemented through a 2-3 tree, in which addition would insertion into the tree would take log n, where n is the number of elements currently in the tree. So since we're inserting a constant amount of elements, that would be the same as inserting one element, and therefore asymptotically it would be theta of log n. For all matches, adding to a tree set would be, you can think of it as calling an iterator on the tree set and looping through every single element, copying every single element into a array list. So since calling an iterator on the tree set would take theta of n, that would be the worst case runtime for the tree set implementation.
Okay, and in getting into our experimental runtime analysis, to answer the first question, yes, certain algorithms are faster than others based on implementation. To start off with the add all method, you can see that right here on the sequential search, that this is the fastest in all the implementation just because of the use of arrays in these in the algorithm as previously explained. And for TST, you also see the same linear pattern for add all, but this time with an increasing runtime, since instead of the arrays, they use trees in this algorithm. For tree set, which these are out of order, sorry, but for tree set, however, you can kind of see a logarithmic runtime where throughout the trials, the runtimes will slowly increase and it will curve off the line of best fit. When you start looking at all matches possesses a linear runtime for the sequential search, again, because of the use of its array list. And on the other hand, for binary search, TST and tree set, they have a constant experimental runtime for all matches. So based on our asymptotic analysis, we theorize that the absolute worst case runtime across all algorithms for the add all method would be in the binary search implementation, and that the absolute worst case runtime across all algorithms for the all matches method would be the same. These actually turned out to be true for add all. However, we do see a disagreement for binary TST and tree set implementations of all matches. In all three of those implementations, we do see a constant experimental runtime. And for add all, for all the implementations, they're the same in both cases in terms of differences. The only visible difference that we really see between the asymptotic and the experimental analysis was in our theorized worst case runtime for the all matches method in binary. In binary TST and tree set, we theorize a worst case runtime of theta of n, but in our experimental analysis, we see a constant runtime for it. And this is actually going to be because in our implementation, we're never going to get near that worst case runtime.